Yes, class, am I audible to all? Isha, Hafsa,
Yes, ma'am.
Nakira. All right. So, class assignments I'll discuss tomorrow. Today, let me just begin with the class and complete this potential energy part. So, we were discussing mechanical energy, where it's the sum of kinetic energy and the potential energy. So, in kinetic energy, we discussed it's the energy possessed by the body due to motion, that is movement. And we also saw the kinetic energy theorem, that is work done is equal to change in kinetic energy. We saw the relationship with momentum also. Kinetic energy is P square by 2m. This is what we have seen. And then we have seen the till here only we have completed, right? Now the types of work done we have to start. Just check, have we written it till here only?
Yeah, ma'am, we wrote it earlier.
Okay. Now there are three types of work done. It's very easy. See, work done is a scalar quantity, so it is not direction dependent. So how can you have different kinds of work done? You'll have different kinds of work done based on the angle between the force and the displacement. Okay. If the angle between the force and displacement is acute, if this angle is acute, so acute angle means theta is less than 90 degree. So that will make cos theta as positive. So work done will also be positive. That is what is the meaning of a positive work done. I'm repeating, this is not a scale, this is not a vector quantity that you have the direction opposite and that's why this is negative or something. Okay. Then you have negative work done, same thing. See, uh, theta is obtuse here. When we say obtuse means theta is greater than 90 degree but lesser than 180 degree. That is what we refer to as obtuse angle. So in that case, our cos theta would be negative. That will make the work done as negative as well. That is what is called a negative work done. Then there's a zero work done. But in zero work done class, two cases are possible. First cases, can you tell me class an angle for which the work done can be zero?
90 degree.
90. Very good, Hafsa. When theta is 90 degree means force is perpendicular to the displacement. Okay, theta is 90 degree. So in that case, cos 90 degree will be 0. So work done is 0. But there is one more possibility. If there is no displacement covered or there is no force. See, this is more important when no displacement is covered. Usually a lot of force is applied in the system. You will see force will be applied. If you don't have any other force, none other than the gravitational force at least will be there. So displacement is 0. So again, when you write work done as force into displacement, so force into 0, that makes the work done as 0. This is also one more possibility. So this is what is meant by work done. Now we have to start with potential energy. For potential energy, there's a small concept of conservative forces and non-conservative forces that we'll discuss. And understand class potential energy, remember it properly, not just for your class 11. Potential energy will come as it is in class 12th also. Gravitational potential energy will come in your chapter 7th and the electrostatic potential energy will come in 12th. Okay, so everything just will be the foundation of it will be built here itself. So write this down, text me done when completed. I'll start with the potential energies basic. Okay, I'll start everything from the basic of it. So whatever trouble you have, you can let me know. All right, please write down this one. Done, mom. Done, mom. Done, mom. Okay, I hope everybody has written. This was a very small, easy part that was left in the last class. Now let me talk about conservative forces. What are conservative forces? Let's say there is an initial A point and this is a B point. Now I am using a path, a force is using a path like this. This is the first path. Second path that is possible is this. This is the second path. And the third path that is possible is this third. So see, different kinds of paths are covered. But if you see, the initial point is this and the final point is this. So the work done that occurs when which is independent of all the kinds of paths that is followed. Okay, where forces are independent of the path followed. They just depend upon the initial point and the final point. So what happens? All the work done are same. Work done 1 is equal to work done 2 is equal to work done 3. That is what is meant by a conservative force. These kinds of forces which just depend on the initial and the final point and not the way the path of the object that has been traveled. These are called as the conservative forces, and potential energy is just based on conservative forces. It is valid for them only. Okay, so that's what has been written as well. Forces in which work done is independent of the path. It depends on the initial and the final points. Like your gravitational force, electric force, elastic force, all the three forces you'll have to study. That's why I said understand potential energy property. You'll have gravitational potential energy and in the gravitation chapter, electric potential energy in class 12th, and elastic potential energy in the chapter mechanical properties of solids. So these are there. Now, a little brief about the internal force and an external force, which I have discussed before also in laws of motion. Like if I have the sun, I have the earth, okay, and I'm just considering them. So right now, my system will be, if I talk, the system that is under consideration for me will be the sun plus the earth. That's it. Okay, sun plus the earth. This is the system that is there. Now, anything apart from sun and earth that is present will be called as the surrounding. And we say we add the system and the surrounding. So whatever was missing from the surrounding has been added. That gives a complete universe. This gives a complete universe. So if any force is existing between them, like the gravitational force or any force, this is known as the internal force. And any other force that acts outside from, apart from the sun and earth, means apart from your system, these are called as the external forces. Now, work done is based on the external forces, not the internal forces. Okay, this I'll tell you again. This part of work done, I'll relate again. Also remember, closed path, the forces is zero. When you're calculating the work done will be zero. This is a closed path. Means initial point is this, and final point is also this. So initial and final points are the same. Okay, body goes from A to B, B to A. Work done by the conservative force is zero in a closed path. This is known as a closed cycle also, or the term closed path is also used for it. And this is
Ma'am,
the
what is conservative force?
conservative forces,
Yes, ma'am.
the forces that do not depend upon the path traveled. Okay, they just depend on the initial and final point. They are not concerned with how the final point has been reached. They just see the initial point, they see the final point. If that's same, work done will be the same because the forces will be the same. So such forces are not dissipative in nature, they are conservative in nature. They remain conserved, they just change one form to another. These are conservative. Like the friction force, it's a dissipative force, it dissipates in the form of heat energy. So that is not a conservative force, it's a non-conservative force. I'll tell you the non-conservative right here. If let's say, if I have, this is A point and this is the B point. So this is how the first body has traveled. This is how the second body has traveled. And this is how the third body has traveled. So according to the non-conservative forces, they depend upon how the path has been traveled. If initial point is this, final point is this, so it will differ. All the points will differ in the sense work done in all the cases will be different. So work done equal to work done 2 equal to work done 3 is not applicable here. These are not equal because they are not conserved. They don't take one form to another. See, they do take one form, but they are dissipative in nature. These are dissipative in nature. So one good example is the friction force. Friction force just converts itself in maximum cases into heat energy. So it is not a conservative force. Okay, it's a non-conservative force. It depends how the path has been traveled, not just the initial and final point. See, this is your initial point and your final point. If the object just relies on these two, it means the force is a conservative force applied. If it doesn't, it means it's a non-conservative force. Now, have you all understood a little bit about it?
Yes, ma'am.
Yeah, ma'am.
With usage of words, no, these will be clear. With usage of words, with usage of the energies and all. Now, the work done part, okay, this I'll tell you later. Yeah. I'll tell this work done thing that I was telling. No, this one, internal, external later. You write it till here, then I'll discuss it with you. Okay, I'll discuss that work done part again. Write it first. Have you all written this page?
Yes, ma'am.
Have you all written?
Yes, ma'am.
Yeah, ma'am.
Okay, all of you have written. Let me start with potential energy. Now, see, in your ninth class and all of your lower classes, the definition of potential energy was just that the energy that is possessed by the body when there's a change in position, change in size, change in orientation, configuration, that is when we have the potential energy. Now, see, that definition is for your lower classes only, and you will not be able to solve numericals based on that definition. Okay, so definitely that is correct, but that's just one part. Remember, you have to focus on conservative interaction. Now, what is meant by this? Conservative part represents the conservative forces. Conservative forces. So, what is meant by this? Interaction also means forces only. Forces getting interacted. So, understand this carefully, class. For if there is a force getting exerted in your system, force is there. Okay, one object is able to exert force on the other. There is a conservative interaction. Now, when I say the term interaction, interaction means like we are interacting, like two-way interaction, one-way interaction. So interaction means two people when they interact, right? When they communicate. So for in terms of the forces also, both the forces should interact. Now, if I just take a block of mass and let's say the normal reaction is occurring, downwards mg will be acting. Okay, so this mg will provide the gravitational potential energy. Okay, only one gravitational potential energy. But if I bring another mass, let's say I brought another mass, now it will also have its normal reaction, have its gravitational energy. So if these two are able to exert forces on one another, there will be a potential energy between them also. See, for potential energy, you just see one thing, conservative interaction. Conservative interaction means conservative stands for your conservative forces. Okay, so conservative part means the forces. Interaction means the objects are both the sides are able to exert forces. Like if I say m1 is one mass, m2 is another mass. They both are separated by a distance of r. Now they both will be able to exert force on each other. Let's say F1 will be there from here, F2 will be there. So F1 will be G M1 M2 by R square, that we'll see in the gravitation. But since they both will be able to exert forces on each other, we will say that there will be a potential energy in the system. This will just give you a hint whether a potential energy in the system exists or not. So it will give you a hint that yes, a potential energy does exist in your system. Or one more example I'll give you from your 12th part. Let's say this is one charge Q1, this is another charge Q2, and they both are separated by a distance of R. Now, this will be able to exert an electrostatic force on this, and this will be able to exert electrostatic force on this. Now, both the forces are there. Conservative forces are being applied, and there is an interaction between them. Interaction means the interaction simply means forces are being exerted, because that's how non-living objects can interact. So interaction means two forces are being able to exert. So potential energy will be there in your system. Like this, you'll have to identify. First, you check, are the forces existing? If then you check, are they conservative? Like you cannot take two friction forces and assume potential energy to exist. So if they are not conservation, conservative. Conservative. Okay, if they are conservative or not. Yes, then definitely a potential energy will be there. And potential energy is basically the work done getting stored. See class, there's a very famous equation, famous sentence that you must have at least heard, all of you. Have you heard of this? Energy can neither be created nor be destroyed. It's a very famous equation,
Yeah,
yes?
ma'am.
So this basically means you cannot add on energies in your system. You cannot take out some energy and just destruct it. That means energies just convert their form. If kinetic energy is there, let's say a moving ball is there at a very greater height, it is moving and then it is dropped. So entire kinetic energy that was present, now where will it go? It will convert it into potential energy. So all these things we'll see in the conservation of energy in detail. Right now, I'm not going into that detail. So, but remember this in the back of your mind that conservative forces will be there and you will have potential energy in that manner. And this definition definitely exists, change in configuration size. Okay, so work against the conservative force, it gets stored in the form of potential energy. This is what I was referring to. Work done will be stored in the form of potential energy. Potential energy gets stored in the form of something else. That energy will be stored in the form of something else. Like this is how the energies, they just change the form and exist. Now, work done by the non-conservative forces, they will dissipate as heat, like the friction force, your viscous force. Now, talking about the internal forces and external forces, which I was mentioning. See, when we talk about the work done here, work done gets entirely stored in the form of potential energy. But as we have studied, work done is due to forces and the subsequent displacement produced by them. Correct. So when I talk about these forces in detail, these forces are basically the external forces. Okay, the external forces that are acting, not the internal forces. Now, what if you just have the knowledge about the internal force that is acting? Then what will you do? So for the internal forces that are acting, you will just do one thing. If you don't know the if you know the external and you don't know the internal, simply the external will be negative of internal, or whatever is given, you can use internal is equal to negative of external. This is how you can use, and work done will be taken of external only, and potential energy will also be taken of external. There's a concept of work potential energy theorem also, like we had work kinetic energy theorem. See, this also means that when you have 2 points, let's say A and B are the 2 points. This is the potential energy at A is UA and potential energy at B is UB. So change in potential energy will be final minus initial, that is UB minus UA. Let's say this is the initial and this is the final. Okay, like this. So change will be this. Entire work done by the external force will be equal to this change in potential energy, like we had kinetic theory. But see, work kinetic energy theorem will require your derivation. Here you don't need that. Okay, here you don't need the derivation. Just remember it and we'll use it in the formula wherever needed. Like a formula, treat it like a formula. So now what the work potential energy theorem says, potential energy difference is work done by external force. Okay, this is the work done by external force, or negative of work done by internal force. As I told you, these are negative of each other. So work done, if these are two negative of each other, you can say work done by external is also negative of work done by internal, or you can just exchange the minus sign wherever required. Okay, or negative of work done by internal in carrying a body from initial point here to a final point here. Yes, tell me class. Still here, have you all understood everything?
Yes, ma'am.
Yeah, ma'am.
Hafsa, Ikra,
Yes, ma'am.
Hafsa, it's clear to you?
Yes, ma'am.
Okay, write it down. If there's any trouble, please let me know. Clarify it, because these are your basics theoretical concepts. Okay, please start writing.
Can you scroll up for a second? Done, ma'am. Thank you.
Done?
Yeah, ma'am.
Yes, ma'am.
Okay, now there was a specific formula of gravitational potential energy that you all have done. MGH, remember? MGH, anybody?
Yes, ma'am.
So
Can
that is
we?
actually, yeah.
I want to write that.
Yes, Hafsa?
A theorem I want to write. Yeah, yes, ma'am. Yes, ma'am. Done.
Okay, so this is what I was saying, that there was a formula MGH which we usually do in the lower classes. So that's you all must be knowing. Now see, that is not actually the standardized formula of gravitational potential energy. That is just one specific case. What I told you about the forces and the work done, that is important for you. Okay, so gravitational potential energy, that MGH formula is just one specific case. When you have an object, you take it to a certain height h, that's it. So why? Because see here the force that acts is the gravitational force, which is mg. This is the gravitational force. This is the force mg, and the displacement, that is h. So work done becomes mg h. That's why we have this formula. And see, the work done gets stored in the form of potential energy. Therefore, we have our potential energy as MVH. So this is just one specific case. We'll do this in detail in the chapter gravitation, but since this is a part of the work done and this involves the work done and work potential energy theorem, so that's why I've written it here also. Otherwise, we'll do this in detail in gravitation. The complete formula is this. This isn't the complete formula. What if you're calculating from the center of the earth? Then you'll have to include the radius of the earth as well. So that will, in that case, the height will be h plus r. What if you're bringing down an object? So there can be many cases in that. So this is just a small glimpse that I'm discussing, because many a times, if you have your test and half yearlies and all, so questions can be there. Aisha, were you asking something? You unmuted yourself.
Yeah, mom. What's the U you wrote for potential energy?
What is the
The U you wrote. U is equal to mgh. Is that a symbol?
U? Yes, yes. Potential energy is represented by the symbol U. Kinetic energy K or KEU, right? But potential energy is represented by the symbol U. Sometimes you can write it as PE also, that is also correct, but U is the symbol for potential energy. Okay.
Okay,
Now,
mom. Thank you.
in potential energy, we usually take a zeroth reference line. Like in graphs we take, or in number lines we take, there's a reference line, and everything beyond the reference line starts to become negative, starts becoming negative. And you have the positive part on one side. Similarly, for potential energy also, you can assume a zeroth of the potential. Now there are it's just a combined club question here. This is the zeroth of potential energy. This is the displacement from here. This is the displacement from here. So the body has been raised in the first part, A part, potential energy at A. This is mgh. Now mass is 2. The mass is 2 kg. And G is 10. But again, you have to take it as 9.8 only unless stated. And that makes it 100 joule. So m, g, acceleration due to gravity, and h. Now B point, see, this is below your zeroth line. Okay, this is below the reference line. So here you'll have mass as 2, g as 10. 10 means 9.8 unless stated, but displacement will be minus 10 because this is below your zeros. This is your zeroth line, like the origin of the graph. So this becomes your origin of the graph. Treat it like your y-axis. Above the axis we take it as positive, and below the axis we consider it negative. So this will be minus 200 joules. And look at the C point. This is exactly on the reference line. Okay, this mass is on the reference line. So here straight away it will be 0 because your height is C. So potential energy is here. So a small question from your gravitation chapter only I have taken. There we'll do this topic
Ma'am,
in
in this gravity also zero, right? See,
where? C part.
there's no gravity, right?
Yes, there is no gravity. Gravitational force is acting. See, this part, C part, you're seeing gravity or the
Yes,
potential energy?
no, ma'am, gravity I'm asking.
Gravity
In
is
C,
acting. Gravity is acting. See,
ma'am, how?
gravity is acting because
Horizontal way, na, right?
center, this is the surface of the earth. The gravitational force is exerted from the center of the earth. Okay, so it is pulling it. That's why it is stable. Otherwise, see, this is
Okay.
the gravitational force, it is pulling it downwards. Otherwise, the normal reaction would have been so high, this would be flying up. But gravitational energy is pulling it. Okay, imagine you are sitting right now at your place. You are on the surface of it. You are not at any height, 5 meter or below the earth, 10 meters. You are we all are at this point C only. Gravity is acting. Gravity acts from the center of the earth. That's why if, see, we'll do all these things in gravitation chapter. Whatever objects are there, buildings are there, trees are there, everything that is present on the earth like this. See, everything is being pulled on the center of the earth. That's why we all are in the state of rest and all, and we all are not experiencing weightlessness. When is this possible? If the air is cut, there is no air, it is vacuum, it's space. So in space there will be no gravity, so the object cannot stay at rest like this. It just flies. You must have seen videos of astronauts and all. It's like they are flying. So the reason is that there is no gravity. Here, gravity is there from the center of the earth. If there is no gravity, how the object should be still? Got it? It's from the center of the earth exerted and throughout uniformly. Okay?
Okay, ma'am.
Okay. Write this part down as well, class. Have all of you written?
Yes.
Okay then. See class, there is a topic spring mass system. This will come in SHM also, simple harmonic waves. But see, whatever things are connecting now that I tell you together, like circular motion also we did together. Because at the end when you sit to study, you will not be able to have a single time to segregate the concepts. So you should be able to make your notes properly so that when you study them at the end you have every note together so that you can revise it quickly, because syllabus is very vast in class 11. Now see, spring mass system means a spring is there and a mass m is attached to it, and this will help you remember this properly. This will come in SHM. So see, this is the mean position. Mean position means the resting position. Okay, resting position. Resting position means the starting position. Starting position, so resting position means no force is acting in the body. Resting position. No forces acting on the body. Okay. Now, if I compress the mass, it means like if I compress the spring, so there will be a displacement produced from the mean position. There will be a displacement produced. Look here, look at this figure, this third one. This was originally where the body was placed. Now, if I compress it, there's a displacement produced inwards. Or if I elongate the spring, means if I pull out the mass. See, you have your mass, you are compressing it. So it's like if this is the spring, this is the mass. So this will compress it, so there's a displacement produced. And even if you're elongating, so there's a displacement produced, right? So displacement, remember, these are the displacements we are taking from the mean position. Okay. Always you have to take the displacement from the mean position. This is like your reference line. This is the zeroth of the potential energy. Now, the force with which you are pulling or pushing the mass in order to produce a displacement, that is your external force. Remember, in your system, there will always be a restoring force that will act, and the restoring force will be acting directed towards the mean position. It will try to bring the object back to the mean position. Okay? The restoring force work will be to bring the object back to its mean position. It's not just for the spring mass system. In SHM, we'll see lots of system. Pendulum and bob is there. You just disturb the mean position of the pendulum. The pendulum comes back to its mean position. If you take a thread and a pendulum, you disturb it. It will come back to its mean position, because there's always a restoring force or a restoring torque acting. Torque we haven't done, as it's the rotational force and rotational motion we'll do. Okay, so these are the rest of the things that are written. And direction of restoring force is opposite to that of the mean position. This will deal with. This is a complex line. This, instead of this, just remember that the direction of the restoring force will be towards the mean position. Now, X is the displacement produced. Remember, the force, this external force, is directly proportional to the displacement. Means more is your force, applied force, more is the displacement produced. This is a little concept from your second book only. So this is not something new or out of your syllabus. You will have to do it. But to understand some things, you should know the basics. So restoring force is directly proportional to displacement from the mean position. So the equation that we obtain is F is equal to minus Kx. This is the equation of SHM, where F is the force which is acting. Minus sign depicts that force is directed towards mean position. Directed towards the mean position. This is the negative signs meaning. Okay, K is the spring factor. This is known as the spring factor. Spring factor means the constant. And in the case of a spring, it is called a spring constant. So you just remember it as a spring constant. What is spring factor? That I'll tell you in SHM only. And X is the displacement. But remember, this displacement is from the mean position. Now, this was a little bit part from your SHM. Why did I discuss this? Because F is equal to Kx will be used in the potential energy of the spring mass system. That's why I just used the whole concept of spring mass system. Basically, remember, right now I just want you to know F is equal to Kx. Tell me, till here, have you understood a little basics of it? SHM?
Yeah, ma'am.
Any queries still here from this topic? All clear?
Yes, ma'am.
Okay, Hafsa, Ikra, what about you both?
Ma'am, what is spring factor?
Yes.
Okay, Ikra. Spring factor, Hafsa?
Yes, ma'am.
Spring factor basically see in different systems. No, spring factor means spring factor when it is used, this means the constant for different systems. Like if we have a pendulum bob system, a pendulum is there, thread and a bob system is there. So the spring factor is basically these things are calculated experimentally, like what's the constant. So constant has been named as a spring factor, which is a general term for all the constants. Like in the pendulum, it is 2 pi. So in the dimensional analysis, we derived equation. Remember, T is equal to K under root L by G. In this, the value of the spring factor K is 2 pi. So actually the formula is 2 pi under root L by G. So like this, various systems are there. So the general term for the constant is known as spring factor. But just for the spring mass system, that constant is called a spring constant. Likewise, for different systems, the spring factor has a different name. It's just the constant that comes when the force is proportional to displacement. Understood?
Yes, ma'am. Ma'am, is can be dependent on the different spring?
It what?
Spring can be vary.
It depends on?
Different spring, like if spring is different, so it will vary.
Yes, definitely it will differ. For every system, see, every spring has the elasticity. Different springs will definitely have different values. So these constants are provided to us. We don't have to calculate them through any method. These constants will be given. Okay, for different springs, they definitely will be different. It depends on the length of the spring, the material used in the spring, the pitch of the spring, everything. Okay.
Okay, ma'am.
Okay then. Before we begin the derivation, or let us just complete the derivation. It's a small derivation. The mass is there, the spring is there, and the mass of the block, this block basically has been stretched up to a distance x. Now work done in stretching the spring from 0 to this x point. Now look, constantly at all the points the work is changing. So the formula that we should use for work done will be the variable one. Remember here F is equal to Kx. Minus sign I'm not taking because I'm just taking the magnitude. Minus sign, we know it tells that restoring force is directed towards the mean position. So work done is equal to F dot dx integral from 0 to x. That's what we are doing. Let's put the value of x here. So work done will be equal to kx dx integrating from 0 to x. Now k is the spring constant. Here in the spring mass system, it's the spring constant. So if it's a constant, it should be taken out. X, see x to the power again. X to the power n is there. This becomes x to the power n plus 1 divided by n plus 1 from 0 to 0 to x in this case. X to the power n plus 1. Now when only x is given, that means its power is 1. So x to the power 1 plus 1 becomes x square. X to the power 2 divided by 2 from 0 to x. Now we put the upper limit here. We put the lower limit here. So work done will be k by 2 x square minus 0 square. Now this is simply equal to half kx square. Now, according to work potential energy theorem, work done is converted to the change in potential energy. So potential energy is basically half kx square. This is the potential energy of a spring. It's the potential energy of a spring. Okay, clear? Easy derivation, simple integration. All right, please write it from here. And if there's any trouble with any part, please ask. Okay, write it.
Mom, what does frestoning mean?
What, Aisha?
What does frestoning mean?
Rest or restoring force?
The frestoning that you've written. The second point.
This one.
Yeah.
Oh, this is F restoring, means force restoring.
Sorry.
Okay.
Okay, Mom, got it.